Um, Welcome back, everybody. So this is our this is our last regular lecture day, and the aim today is more to give you a kind of repetition of the Lagrangian formalism, and then we're also going to look at examples. And the final project, or what we might call just a final, is going to contain one exercise with Lagrangians. And it's going to be a kind of lookalike of what you've seen till now, and perhaps today as well. The other thing today, if you wish to hang around and discuss the homework number 9, which we put a due date for tomorrow, I mean, feel free to do so. And the same with homework 10, which actually gives you an additional score of 10% on top of everything. So both the two last ones are actually paper and pencil exercises. There's nothing numerical there. And then on Friday, the plan on Friday is to make a summary of what we've done. I'm going to bring in some summary elements today as well. And then we can start looking at the final if you want to. And then you can just hang around as long as you want. The final will be available on Friday in the morning at 8 o'clock. So if you have time to peep into it, do that if you feel for it. And then you could just come and discuss on Friday. So I'm gonna do a kind of summary in the beginning, and then we can use the rest of the time to look at the final project. And that's going to be a kind of, how to say, a lookalike of the midterms and the weekly assignments which you've been doing. And as you've probably seen, I mean, I don't like to sneak in, how to say, nasty questions. So hopefully it should be pretty straightforward. I mean, the homeworks which we have now, 9 and 10, they are more on the paper and pencil sides, and perhaps a little bit more difficult than what you've seen, but it's more you bringing together many of the concepts which we have been looking at. So I'm going to switch over to the whiteboard and go through some examples and repeat a little bit about the Lagrangian formalism and try to motivate again why this Lagrangian formalism is so useful. And for many of you who will continue with physics, as we said, I mean, you're going to encounter that, and many of you actually take the graduate course in mechanics, and there you will actually start with the Lagrangian formalism. That's a typical starting point when you want to bring in more mathematics in a physics course. So this course is a kind of mix between the graduate classical mechanics course. It has some of the elements, but it has a lot of elements which you've seen back in 183. Okay, so let's switch over to the whiteboard and look at some final examples on how we can use the Lagrangian formalism and why it's so interesting. So one of the things which we did on Monday was actually to look at, so let me just quickly repeat that. So a quick repetition from Monday. So on Monday we looked at the pendulum, and the case which we had was just a plain, simple mathematical pendulum. So let me quickly repeat that because that links also with homework 9. And what we did then was to simply look at the system in 2 dimensions. And we had the y and the x-axis along here. And then we had a rod here which kept this pendulum. So this is a rod which has a fixed length. And the length of this rod is kept fixed, and it's called L. It has a mass m. There is a tension force which acts in the opposite direction, and then we have the gravitational force. So I'm just going to put vector signs on these. Fg for the gravitational force. And the type of equations which we ended up with was to start with a Lagrangian, where we actually defined the Lagrangian in terms of polar coordinates. So we made a transformation to polar coordinates, which is the kind of equations you will often encounter the pendulum rewritten in terms of, and then we had an x and an r times a sine of phi. So we have this angle phi here. And then we defined a Lagrangian with a constraint. And this Lagrangian is a function of the absolute value of r, which is fixed. We have the r derivative. And since r is a constant, it means that its derivative has to, as a function of time, has to be equal to 0 because it's just a constant. So the length of r doesn't change. This is one of the assumptions behind this model. And if you look into textbooks on the pendulum, you will see tons of complications. You can have the double pendulum, which probably many of you have seen, or you could actually attach a spring to the rod, and then this would vibrate up and down, and then you would have the rod which would swing, and then you would have the spring which makes it vibrate. So that's just to complicate things, but it's pretty easy when you want to solve these problems numerically, because numerically you just have to identify the equations of motions. And if you start with a Lagrangian, it's pretty easy to actually set up the equations of motion. Okay, so let's just remind ourselves of these things. So we rewrote it in terms of these quantities. And then, in our case, the Lagrangian was given by the kinetic energy. And I'm going to remind you quickly of how we arrived at this equation here for the kinetic energy, because this is easy to forget. And then we had the potential energy, which is minus m times g, and then we are replacing y with r times cosine phi. But then we had the constraint, plus a lambda multiplied with r minus L, because we're forcing r to be equal to L. And when we solved the equations, what we found then is that we got back the classical equation for the angular acceleration, which was given in terms of minus g divided by L. And this is something we have met before. But then we could also show that this lambda has to be interpreted as a tension force, this force T, which we wrote down, and that's given in terms of the angular velocity plus m times g times a cosine of phi. So that's to be interpreted. This constraint which we put in actually gives us the equation for the force, which counteracts the gravitational force. Now, let's quickly remind ourselves on how we actually got here. So this is a two-dimensional case. So this is a quick reminder. And we did this derivation a little bit early in the semester when we started with the two-body problem, and we rewrote everything in terms of the polar coordinates. So we would typically start with an equation like this, where we have the velocity in the x direction squared plus the velocity in the y direction squared. And now you've gotten pretty familiar with that, because when we looked at the solar system, you were looking at conservation of energy, and then you needed the magnitude of the velocity, which then was simply vx squared plus vy squared when you wanted the velocity squared. So this is a quantity you would have typically in Cartesian coordinates. And then when you transform this to polar coordinates, then you got the expression which we have on the top of the whiteboard. And I just wanted to quickly remind you of how we got to that expression, because I had the discussion with people, and it seems that this is some kind of forgotten wisdom, and it's useful to see it again. So I'm sneaking in now and then some elements of repetition here. So this is also useful to have seen again, because this is a kind of transformation which is very useful to look at. So what we did in the previous case was actually to set x. We had x equal to r times cosine phi when we did this in 2 dimensions for the two-body problem. So it's not exactly the same in the same way as we did it for the pendulum, but it's basically the same operation. You get the same equations actually. So what we need is then dx dt, which is equal to v of x, and that becomes d of r, and then we would have a cosine phi and d dt. So we need to take the derivative of both r and the angle phi. And similarly, what we had for y, this would now become d of r times sine of phi of d dt. So if I now square these, so this quantity, when I now want to, if I want to square them, that is clearly given by dx dt squared. And if I write out the expressions, this simply means that what I'm getting now, when I'm taking the derivatives, I get a derivative if I look at d of r of cosine phi of dt. This is obviously equal to d of r of dt times cosine phi. But then I get a minus, and I get a sine phi, and then I get multiplied with a d of phi dt multiplied with r. So that's the equation which I'm now going to square. So that means that if we now put this in parentheses here, it means if we bring these equations, this equality sign here, what we are going to get then, when I just replace this with r dot and this with phi dot, then when I square it, I simply get r dot squared cosine phi squared. I get a plus an r squared, and then I get a dot phi squared, and then I get a sine phi squared, and then I have a minus 2 times r of phi dot, and then I have a cosine phi times a sine phi. Now, when I do the same with dy, and I'm not going to put in the intermediate step with setting out the derivatives, but what you get then is an r dot squared times a sine squared phi, and then I get a plus an r squared phi dot squared, but now I have a cosine phi squared, but then I get a plus here of 2r times a phi dot, should be a dot here, times cosine phi of sine phi. And you see now that when we add these two terms, when I want the magnitude of the velocity, then I have vx squared plus vy squared. And you see now that I get an r dot squared cosine squared phi plus sine squared phi. That gives us 1. And I have the same with r squared and phi dot squared. And then the cross terms with cosine phi and sine phi, they cancel each other. So what we end up with then, when we bring everything together, then what we have is that dx dt squared plus dy dt squared, which is equal to vx squared plus vy squared. That becomes simply equal to a term which goes like r dot squared plus r squared multiplied with the angular velocity squared. So this was just meant as a quick reminder about the kinetic energy when we make the transformation to polar coordinates. Now, if you're dealing with spherical coordinates, you will obviously need another angle, and not just an additional small complication to what you've seen here. Now, the reason why I wanted to bring this up again is that I wanted to take a look back at this potential which we had in homework 6, the so-called Lennard-Jones potential. And now we're going to look at how we can use the Lagrangian formalism on that specific case. And it may happen that you will encounter this homework 6 again in the final. So I'm not going to calculate the final for you, but this potential may pop up there. I haven't made up my mind yet. So, but it may be there. I actually had a teacher in mechanics when I started, who everybody has a reputation that he would actually calculate the exam the day before the exam. And the year before us, I mean, the external examiner couldn't correct it because there was a typo, but all the students had the right answers. So is a small hint of what you might, or what you may encounter. So let's look at this example with the Lennard-Jones potential which we had, because that brings in some further elements of repetition. Now, the potential which we looked at then is a famous potential in physics. It is a potential which is a parametrization. So this is a Lennard-Jones V of R. And you encountered this, I think it was back in homework 6. It may have been homework 6 or 7, I don't remember exactly. And this runs like a constant V0. And then it has a term with one constant here, then it has a R here to the power of 12. And this is a potential which has been fitted to reproduce the interactions between argon atoms. But you can also use it for other types of systems in atomic and molecular physics. You can use this in quantum mechanical studies, but you can also translate a quantum mechanical problem into a classical one by treating this as a classical potential, and then simply just look at an Newtonian type of equations of motions, where you have a potential which is not a fundamental force, but it is a potential which now has been parameterized, and where you have frozen out all the quantum mechanical degrees of freedom. So you can think of this as a kind of effective potential, which is used in so-called molecular dynamics calculations. And molecular dynamics is used to simulate materials at finite temperature, but it's also used in the pharmaceutical industry to actually model the way the DNA interacts, or molecules interact. So this type of potentials are something which are very much used in physics and in quantum chemistry. And this would, if we have two particles, it would just be this R is the absolute value of the distance, the relative distance between two objects. Now, if you look at this one, this is like the Coulomb interaction which we had, or the gravitational interaction or potential. And what you notice here is that there is no dependence on any other variable than the relative distance and the magnitude of the relative distance. So that means there is no angular dependence here. And that really saves a lot of, complications for us when we are setting up the equations. So if we are using this type of potential, we can now define a Lagrangian for this potential, and this potential looks something like this. So it has a minimum, and I think you may remember this back from that specific homework. And there's a minimum here, an R min. And here we would expect circular motion. You could obviously give this a higher energy, and then you would get elliptical motion. Or, as you can see here, the particle could actually, or these particles, could actually escape this potential well. So you could get into a parabola as a motion, or hyperbola as a motion. So this is actually something which is a lookalike of what you've seen before with the gravitational force. But it's something which is normally applied in another context. So that means that what we need to do then, when we are setting up the equations of motion, we would then have a kinetic energy. So we would have a Lagrangian. If we now look at a two-particle system where we have the reduced mass, then this R is actually the relative distance. We would have this as a kinetic energy, and this is based on the same transformation which we did before. And then we would now have minus V of R. When we then are setting up the equations of motions, when we bring in the Euler-Lagrange equations, so we need now equations for the derivative with respect to R. So we have a time derivative here, d dt of dl as a function of the radial velocity, and we want this one to be 0. And then we have also another equation which depends on the angle phi. So this would now contain d dt, and then I would have a d of l of d of the angular velocity with respect to the angular velocity, and that has to be equal to 0. Now, last week, we did actually derive the equations for the angular motion, because you see now that if you look at the potential, if we now take a closer look at it, what you will notice here is that this has no dependence on the angle, on phi. So it means that if we look at the expression which we have now for the kinetic energy, so the kinetic energy does not contain an explicit dependence on phi. The potential does not contain an explicit dependence on phi. So that means that this partial derivative of the Lagrangian with respect to phi is equal to 0. So what we have in that specific case, if we look at the last equation, in the last equation here, so if we take this one, what we have then is that d of L, d of phi is equal to 0. And what also happens then is that this means simply that d dt of d of L of d of phi is equal to 0. And last week, we actually found that this term which you see here is the same as a torque. So what this ended up being, and so I'm just repeating what we did last week, is that we have a d dt when we now look back at the Lagrangian and we take the derivative with respect to phi here. When we take that derivative, what we have is simply a term which goes like 2 times phi derivative times r squared times mu times a half. So what we are going to get then is simply the following expression. So we are going to have this one, m times r squared and dot phi. And we know that the phi, the derivative, the angular velocity, is something which is equal to the angular momentum divided by m. Sorry, this should not be m, it should actually be mu, because I used the term mu, the reduced velocity. And we know that for this type of force, this term here, phi dot, is actually equal to L divided by mu times r squared. So that means that what we have is actually conservation of angular momentum of d of L equal to 0. This could not have been the case if we had had a force and a potential which would depend on the angle as well. So when you see a potential like this Lennard-Jones potential, you can actually now, with the wisdom you have, you could say that this is a force where angular momentum is conserved, and the equations of motion in the angular direction, they just simply reduce to stating that angular momentum is conserved as a function of time. So that's an extremely useful thing when you have this type of conservative forces. And if you have only a dependence on the distance between two objects, or the relative distance, then this is something which leads to angular momentum conservation for at least a two-particle problem or a many-particle problem. So when you see something like that, you don't need to run any calculations. You just know that this has to be the case. Now, the other thing which we end up with is actually the equations for d of L, which we need to set up. So d of L, d of R. If we go back to the equations which we have, what we see now is that there is a dependence on R in the potential up here. So this is going to give us a dV dr. And there's also dependence on R in this equation here. So let's just set up the derivatives. So this gives us, when we look at this one, we're going to have an R times mu, and then we have phi dot squared. And then I get plus 6 times V0. And then I have a derivative of the potential. So this is going to be 2 times 8 to the power of 12 divided by R to the power of 13. And this is going to be minus B to the power of 6 divided by R to the power of 7. And then the next thing I need is to find dl of dr dot. And this is simply going to be given when I go back to my Lagrangian, if you now look at that one. So we have an R dependence here. So that's going to give me 2 times R dot, and I have a half times mu. So that's simply going to give me a term which goes like mu dot r. And then I take the second derivative, no, the time derivative, sorry, not the second derivative, of mu times r dot. We assume the masses are conserved. They don't vary as a function of time. So this is simply the radial acceleration. And this has to be equal to minus this other term which we put up. So that means that when I collect everything now, what I get is that mu times r dot is simply equal to mu times this term r times phi dot squared plus 6 times v0. And then we have the potential here, which we plugged in. So this is 2 times a to the power of 12 divided by r to the power of 13 minus, and then we have b to the power of 6 divided by r to the power of 7. And this is my equation for the force in the radial direction. And in this specific case, if we now were to go back to the gravitational force we had, this is a type of potential where we don't have analytical solutions, unfortunately. So here, we would actually have to solve everything numerically. So that's a typical example where we can use the insights we have, but we would have to revert to a numerical solution. Now, I wanted to show you another example, which is also pretty neat. And it's a kind of example which extrapolates to actual applications. So let's try to look at a system which is a little bit different from what we had, but it allows me to bring in oscillations again, which is another topic which we have been looking at. So let's take a new example. So we have an example 2 here. And let's look at, instead of looking at a coupled pendulum, we could now look at a coupled harmonic oscillator. And this is a case, so one of the reasons why I bring it up is because you're going to encounter this kind of modeling of physical systems in many, many occasions. So the example we are going to look at is an example which is a little bit simplified. So we are going to look at the 1-dim model for the carbon dioxide molecule for CO2. So the way we can think of this now is as follows. So you could now, if we now think of a one-dimensional system, so we have the oxygen atom here, and then we have the carbon atom at the center here. It's actually not larger, it's smaller physically. And then we have an oxygen here, so let me just write O, this is carbon, and this is oxygen. And we could now assume that this has mass m, this has mass m. So this is just a simplification we are making now, and this has mass 2m. And the reason for this choice is that this allows me to set up a simple analytical model, which I can actually solve analytically. But you could equally well solve this numerically if you wanted to. And the way we can model this is by setting some spring forces in between. So there would be a distance from origo here, from the origin of x1 here. You have a new distance of an x2, and then we have a final distance of an x3. Now, keep in mind that this is a very, very simplified model, but one way of transferring this to more realistic cases is actually if you look at a solid or a material. So if you're thinking of a material, in the more realistic cases, you will often find some kind of lattice structures. So if you think of a material, which is where you have a, let's say a crystal, which is shaped as a cube, and you could think that in every site here, there is an atom. And one of the physics models, the simplest possible physics models which we can set up, is actually us having these atoms being connected with a spring force, so they can vibrate around a minimum position, like this. So you could make a simple model for a material at a given temperature if you don't want to deal with the basic quantum mechanics, but you could now think of these atoms or molecules interacting just via spring force. Now, when I say spring force, and I'd like to see if I can trigger your intuition a little bit here. If you think back to the discussions we had about harmonic oscillator potentials, what was one of the mathematical tools which we used to find the expression for the harmonic oscillator potential? Does anyone remember what kind of, we used a mathematical tool to approximate the, yeah?
Like a Taylor series?
We did a Taylor expansion. Then, what we were assuming then is that you would just have small vibrations around an equilibrium position. So the way you could think of these guys is that each of them just barely vibrate around the equilibrium. So at the equilibrium position, the derivative of the potential is zero. So when you do the Taylor expansion, the first derivative is zero, but then you have the second derivative, which goes like x squared. And that's what gave us the spring force. So that's the mathematical tool you would use. So if you think about such systems, you could now think that these are systems at low temperature and that they barely vibrate around the minimum. So then this kind of spring force model is a very useful first approximation to you replacing complicated interactions with just a simple potential. So this is a kind of physics reasoning which we are using here in a way. But there's more to the picture than meets the eye. So when you guys are, if you dig a little bit deeper into earthquake protection, if you think of a house with given store, a house with a given number of stores, so this would be the different stores of a house, you could now think of every store being connected with a spring force. So one of the simplest way of modeling the way a house acts under the influence of an earthquake is that you could think of your house oscillating up and down. So when you live in California, for instance, you know that there are earthquake regulations on the way you build houses. There are barely any such regulations here. And the way actually these houses are protected against earthquakes is that they actually absorb these oscillations. So when you model the houses and you build the houses, you've actually taken into account critical oscillations which the house can be set into. If you exceed what has been modeled, obviously the house may collapse. But a simple model for you setting up the way a house would react towards a kind of shock wave or something like that is actually setting up this kind of simple springs connecting each floor of the house. So this kind of modeling which we're doing here is something which normally enters more realistic modeling of, let's say, earthquake protection. But let's look at the example which we have here. This is a kind of digression. So if we look at the example which we put up, which is a one-dimensional model for carbon dioxide, let's now look at the Lagrangian, which we would have. So the Lagrangian for this specific case would now be equal. So what I'm going to do now is to venture into more, theoretical manipulations, so just paper and pencil manipulations. And since we have one of the masses being equal to 2, then we have a half times 2. So this is for the second position. So that's the velocity of one of the masses. Every single mass here has its own kinetic energy. So we would have 3, this is squared, multiplied with a half. And then we need to subtract. We have a spring force K. So if we go back to the model here, we are now assuming that this spring force has a constant K in both places. The masses are the same. And the reason I'm doing this is simply to simplify the mathematics. So when you set this up numerically, you could plug in different spring constants, different masses if you want to, and make it more complicated. But we are just going to do things a little bit simpler in order to be able to solve this analytically. So we have an x2 minus x1, so it's the potential energy between two of the objects. And then we would have minus k divided by 2 and x3 minus x2 squared. So that's the potential energy. So if you use a Lagrangian formalism, one of the strengths of it is that you can actually set up the energies. So you have the potential energies. You don't need to set up the forces. So when we now derive the equations of motion from Euler-Lagrange equations, we will actually get equations which depend on these different variables. So the next step, which we will typically do here, is actually now to set up the equations of motion. So we would set up the equations for x1, x2, and x3. So we would need this one, x of I minus d dt, and then I need dl dxi derivative, and this is equal to 0. And where these xi's, where this I takes the values 1, 2, and 3. If I now take the derivatives, I will get one equation for x1. So this is the force in the x1 direction. And this is simply going to be equal to minus k of x1 minus x2. I'm going to get that 2 times m times x2 dot, the second derivative, which is simply minus k times x2 minus x1 minus k times x2 minus x3. That's the next term. And we can just rewrite that as a minus k times 2 times x2 minus x1 minus x3. And as you have solved this kind of equations numerically, it wouldn't be any problem for you to go back to the programs you developed for the harmonic oscillator. And instead of having just the motion for one object, you would now simply have a couple set of differential equations. If we had done this, if you guys had had more linear algebra, you could actually rewrite this in terms of a simple linear algebra problem. But this is a little bit beyond because not everybody has taken a course in linear algebra. But let's look at how we can solve this type of equations. Now, this is going to lead to a transformation of variables. So I'm trying to catch two birds with a stone here by bringing in ways of transforming these equations in a simpler form. Because what you see now are equations which depend on the different variables. So these are coupled differential equations. By a new definition of variables, you can actually rewrite these as equations which will depend, where each one will just depend on one variable or at most two other variables. So let's try to do this kind of trick because this is useful to have seen. And one of the things we could do now is simply if we look at these equations, if we look at the first one, this one, it's tempting to define a new variable, which we would call Q1. I'm just going to call it Q because I couldn't come up with a better name for it. I could define Q1 as an x1 minus x2 here. I could define a Q3 as an x3 minus x2 here. But then I have the problem with the equation in the middle for x2. And one of the things which I'm going to do now is actually to take and remind myself about the center of mass position, which is simply given by I, in our case 1 equal to 3 of mi times ri, divided by the total mass, which is a sum from I equal 1 to 3 of mi. So if I look at that one, since this is just a one-dimensional problem, what I would get then is that I'm letting my r go over to an x, and this is simply x1 times n plus 2n times x2 plus m times x3 divided by 4 times the mass. And that means that what I have is an x1 plus 2 times x2 plus an x3 divided by 4. And if I go back to my differential equation, what you will see then, if you look at the final expression which you have here, this one, there's something which is a lookalike of what you have here. We need some more manipulations here. So what we can show then is that this x2, when we introduce this central mass position, is given by 4x minus x1 minus x3 divided by 2. I can show that x1 is equal to 3 times this q1 minus q3 plus 4 times x divided by 2. And similarly, I would have that x3 is actually equal to 3 times q3. I hope I've done this correctly. I did double check it yesterday. Like 2. What I can do now, and I guess you would hate seeing me squaring these variables and taking the derivatives. I can rewrite my Lagrangian in terms of this x, q1 and q2. So if I do that, I can now rewrite my kinetic energy in terms of these new variables. So what I would get then, when I set up the Lagrangian in terms of k minus v, by the way, you are not going to get something like this for the final project. So I'm just, this kind of manipulations, I've never been very fond of them, but it's useful to have seen them. So if you look at these equations here, what we have now is that we can rewrite this in terms of 3m divided by 8 of q1 squared plus q3 squared, the dot derivatives, minus m times q1 dot of q3 dot divided by 4, and it contains the linear or the central mass position, the derivative of that squared, and then comes the kinetic energy, the potential energy, which is now minus k divided by 2, and then I have a q1 squared plus a q3 squared. Now the hope with this kind of transformation, and it's pretty common in physics often to try to transform this type of equations. Now, nowadays, when you can do this numerically, there is no point in doing that because you would simply set up a set of coupled differential equations and solve them. But what we could do now is to use the Euler-Lagrange equations and see what we get. So one thing we could do now is simply to set up the equations for x minus d dt of dl of dx dot, and we want that one to be 0. If we look at the equation for the Lagrangian, there is nothing in the potential energy, so there is no explicit dependence on x itself, but there is only a dependence on the velocity of the central mass position. So if we take a look at that one, what we have then, if we use these equations, we are simply going to get that d dt of m times x derivative is equal to 0. Now comes an element of repetition here. If you think of the way we derived this x was the linear not the linear momentum, but the central mass position. If you look at this quantity here, what does this actually mean, what we have here? So we have the central mass position, x. Now we have the central mass velocity, which is x dot, multiplied with m. So what does this quantity inside the parentheses actually represent? M times x dot. Yeah, linear momentum. And what are we stating here? When this is the time derivative 0? It's conserved. Perfect. So this was the element of repetition here. So what we see now from the Lagrangian formalism is that we have showed that linear momentum is conserved. And that's a pretty nice way of actually introducing the conservation of linear momentum. So that's an interesting point. So for the x variable, we have a very simple differential equation. And we know that when we integrate up, it simply tells us that so it says that linear momentum is actually a conserved quantity. So this is actually pretty nice. The final thing which we need to do is actually to find the differential equations for the q's. So we would have a dl dq1 minus d dt of d of l of dq1 dot equal to 0. So if I take the equations for q1, if I now take the Lagrangian, what I'm going to get then is the following type of equation. I'm going to get an equation which says minus 3 divided by 4 of m times q1, and then it's the acceleration for this variable, plus m divided by 4 times q3, and that's equal to minus k times q1. Then I have a q3 equation, which is pretty similar to the other one, except that now we interchange q1 with q3. So that's the acceleration for q3, plus 1 divided by 4 times m of q1, derivative, second derivative. So these are the second derivatives. And this is equal to minus k of q3. Now, we know that these are harmonic oscillations. We have no damping. So here comes the next element of repetition. So if you were to make a guess now on the solutions Q1 and Q2, so these are harmonic oscillators, right? So what kind of mathematical shape would the solution have if you don't have any damping? Yes, which we then can rewrite in terms of just an exponential with an imaginary argument, right? So what we could say now is that we could give a guess and plug that one into the equations in order to try to find a solution. So what we could guess now is that Q1 is given by an A of E of I of omega t, and then I could guess that Q3 is equal to B times E of I of omega t. And what I'm going to do now is to define this omega squared as we did before. I'm going to divide with m on both sides. So this is going to be given by k divided by m. So this is the same thing as we did before. So we don't have any damping, so we know that the solution is a linear combinations of cosines and sines, which obviously has to be can be rewritten in terms of an exponential. So we can actually now plug that in. And if we look at the first equation, what we would get in that specific case, so if we take that one, so if we take the equation for Q1, and I see that my time is actually running out here, it's only 3 seconds left. So I'm going to sneak in just 2-3 minutes on Friday, and then we do the repetition. So then I'm just going to give you the final part of this on Friday. You're not going to encounter these kind of manipulations on the midterm, on the midterm and the final one. But I just wanted to bring this up because what you see here are the kind of tricks you can use when you want to do the calculations by paper and pencil and do this kind of analytical manipulations. But when you do this numerically, it's much, much easier because you would simply set up a couple set of differential equations. Okay, I'm going to stop the recording. Feel free to hang around if you have time. If not, remember that we have office hours. And I also have an office hour in the evening tomorrow from 9 to 10, if you wish to swing by. And also I'm going to hang around here till roughly 5 o'clock. So if you have questions about the final one or this additional one, feel free to do so. So for those of you online, I'm going to stop the recording.